So, we've spent the last few sessions deep in the abstract, really deep.
We have.
We navigated the whole landscape of number theory. We explored the fascinating world of modular arithmetic, the math of remainders.
Right.
And we established the glorious power of what makes these huge prime numbers so special.
It was complex. It felt, frankly, like we were prepping for a pretty high-level math exam.
And that prep work was absolutely essential. I mean, in cryptography, the integrity of a system doesn't rely on hidden tricks or some kind of complicated machinery.
No.
It relies on proofs, on pure, unshakable mathematics. You really, really need that foundation.
Exactly. And now we get to the payoff. Today, we're taking all those theoretical sources, all those concepts of primes and inverses, and we are connecting them directly to the ultimate real-world application, securing the modern internet.
Our mission today is to take a really deep dive into the RSA algorithm, named after Rivest, Shamir, and Adelman, to understand precisely how it works, why it's so secure, and how this one elegant mathematical invention solved the biggest logistical nightmare that had plagued cryptography for, millennia?
For millennia, yes. So to start, let's frame the classic problem. In our sources, cryptology is always sort of distilled down to a triangle.
Okay.
We have Alice, the sender. She wants to transmit her message, let's just call it $2, to Bob, the receiver.
And the third corner of that triangle is, of course, Eve, the attacker, always lurking, always eavesdropping on that communication channel.
Right. So Alice needs an encryption function, let's call it $E, and she uses a key, E, to transform her plaintext message, $2, into unreadable ciphertext, a cryptogram, C.
And then Bob gets it.
And Bob applies his decryption function, $, and his key, D, to turn that cryptogram, C, right back into the original message, $2. The fundamental requirement, the absolute necessary rule for any cryptographic system, is perfect reversibility.
Meaning the decryption has to yield the original message. Perfectly. So D must equal $2. The system has to guarantee that, no exceptions.
It has to.
Okay, so that brings us to the first major category of security, the one that really governed all communication up until, the late 20th century?
That's right, symmetric systems. In these systems, the key used for encryption, E, is either identical to the key used for decryption, D.
Or they're so close that if you know one, you basically know the other one instantly.
Exactly. We can essentially just say E equals D. This is classical cryptography.
And this is the era of classical codes. I mean, they're brilliant for their time, but they really do illustrate the core vulnerabilities that had to be overcome. Let's start with the one everyone knows, the Caesar cipher.
Ah, yes. The Caesar cipher is a simple substitution cipher. You choose a shift value, K, and every single letter in your message shifts K positions down the alphabet.
So if K is 3, A becomes D, B becomes E.
And so on. That shift value, K, is the secret key.
Its simplicity is also its downfall, though. But it's a great teaching tool. What happens if if Eve, intercepts a Caesar cipher message?
Well, the first thing Eve realizes is that the key space, the number of possible keys she has to try, is tiny.
Right. For the English alphabet, it's just 10 X.
Only 26 possibilities. I mean, a determined human can brute force that in a few minutes. A computer, not even a fraction of a second. The method is fundamentally insecure because the key is short and the code is just. It's so easy to identify.
And even if you don't want to try every single key, you can just lean on linguistic patterns, right?
Yeah.
This is where statistical cryptanalysis comes in, the real art of code breaking before computers.
Absolutely. Our sources point out the power of frequency analysis. If you analyze a long enough message in English, you know with very high statistical certainty that the letter E is the most common.
Followed by T, A, O, something like that.
Right. So if Eve intercepts a long ciphertext and she sees that the letter Q appears, say, 12% of the time, she can make a very strong, very educated assumption.
That Q in the ciphertext is probably E in the plaintext.
Exactly. And once you prove that the assumption is correct, you've solved one letter, and the rest of the code just starts to fall apart. You've just drastically reduced the key space.
Which is why we needed more complex encryption.
And that led to things like the Vigenère code, which was a massive leap forward.
Okay, how did that work?
Instead of a static shift value K for the entire message, Vigenère uses a keyword. So the shift value changes with every single letter of the message based on the letters of that repeating keyword.
Ah, so that immediately messes with its statistical problem. If my keyword is secret, the first letter of my message shifts by S. the second by E, the third by C.
And so on. The letter E in your original plain text might get encrypted into 3 or 4 different ciphertext letters. It completely scrambles the frequencies.
So it was considered unbreakable for a while.
For centuries, Vigenère was known as le chiffre indéchiffrable, the unbreakable cipher. It resists that simple frequency analysis, but it's not immune to deeper analysis.
Cryptanalysts eventually figured it out.
They did. They developed methods like the Kościuszki examination and calculating something called the index of coincidence.
Let's explain the index of coincidence because it's a really brilliant piece of analytical thinking.
It is. It measures the probability that if you pick 2 letters at random from a text, they'll be the same letter.
Yeah.
In a totally random string of text, that probability is low. But in normal English, it's much higher, right? Because E appears so often.
Right.
With Vigenère, the ciphertext looks a lot more random than English. But the key insight, the thing that breaks Vigenère, is that if you find repeated sequences of letters in that ciphertext,
Like XQZ appears twice.
exactly, they might correspond to the same plaintext sequence that was encrypted using the same part of the repeating keyword.
So if I see XQZ repeated, and the distance between them is, say, 15 letters, I know that 15 is probably a multiple of the keyword length.
Precisely. And once you find the keyword length, say it's 5 letters, you can then just take every 5th letter of the cryptogram.
And suddenly you have 5 separate, much smaller Caesar ciphers to solve.
You got it. The system is fundamentally symmetric, and that symmetry equals vulnerability once the key is compromised or the system structure is revealed.
So if these symmetric systems are inherently breakable, is there any system that is provably secure, like mathematically bulletproof?
Yes, there is. It's what we call the gold standard of secrecy. The one-time pad, or OTP.
The uncrackable system.
Mathematically, yes. Our sources highlight that this system is absolutely uncrackable.
So what are the requirements for this theoretical perfection?
They are brutally strict, but if you follow them, you get perfect secrecy. First, the key has to be purely random, like generated from a source of true randomness, not a computer algorithm.
Okay.
Second, the key has to be at least as long as the message itself. If Alice wants to send a 1 gigabyte message, she needs a 1 gigabyte key.
Wow. And third?
The key must be used only once, never again. The encryption method is simple. Often, it's just a bitwise XOR operation combining the message and the key.
And the reason it's provably secure is what?
It's because the key is statistically random, so the resulting cryptogram is also statistically random. There is literally no pattern for Eve to find.
None at all.
None. For any given cryptogram, every possible plaintext message is equally likely to be the original. If you get the ciphertext XYZ, you have no way of knowing if the key made the original attack or retreat. You are just drowning in possibilities.
That is theoretical perfection.
Mm-hmm.
A system secure against any computer, even future quantum computers. But, and this is a huge but, this brings us to the devastating, heartbreaking reality that makes the OTP basically irrelevant for global communication.
A key exchange problem.
The key exchange problem. This is the huge logistical problem that our source material talks about. The very requirements that make the OTP perfect are also its Achilles heel when you try to scale it up.
Let's focus on that length requirement.
Please.
If you have to securely transmit a 1 gigabyte key to me before you can send your 1 gigabyte secret message.
The question becomes, why aren't you just transmitting the 1 gigabyte message itself securely in the first place?
Exactly. It's the core dilemma. Symmetric systems require a secure channel to set up the secure channel.
It's an endless self-defeating loop.
For thousands of years, the secure key distribution mechanism relied on physical security diplomats with lockboxes, trusted couriers, high security cables. This is totally unscalable for the digital age.
And the problem doesn't just exist between two people. It explodes when you try to connect a global network.
It's the logistical explosion. Imagine a network of nother users, say the billions of internet users today. If every person wanted to communicate securely with every other person using a symmetric system,
Oh, wow.
each person would need to manage nullion unique secret keys. The total number of keys in the system grows quadratically. It's proportional to null or squared.
So even just a network of 1 million users would require nearly 1 trillion unique key pairs to be generated, distributed, maintained.
And if you're using OTPs, they don't need to be replaced after every single use. It's a logistical impossibility.
So symmetric systems were provably secure, but practically useless for the internet.
Completely useless for large-scale decentralized communication.
Right.
Cryptography had hit a total dead end. They needed a breakthrough that just eliminated the physical transfer of keys altogether.
And that is precisely where the revolutionary thinking of Diffie and Hellman just changed the game forever. They proposed this radical, really counterintuitive solution: public key cryptography.
Or asymmetric cryptography.
Right.
And the genius was the paradigm shift. It was, if the key distribution is the problem, let's just solve key distribution by removing the need for a secret exchange channel.
So how do you do that?
They proposed splitting the key function into two mathematically linked but distinct parts.
A pair, the public key, E, and the private key, D. How did they envision these two keys interacting to solve that key exchange nightmare?
The fundamental insight was separating the power of encryption from the power of decryption. The public key can be broadcast to the world.
You just post it online.
Post it online, print it in a phone book, whatever. Anyone can access it. Its only function is to encrypt messages destined for Bob. It's a one-way street.
And the private key, that remains Bob's secret.
Only he possesses it. Its sole function is to decrypt messages that were encrypted using his corresponding public key.
And that separation is what solves the logistics. Alice wants to send a secret message to Bob. She just looks up his public key, E encrypts the message, and sends it over the open, insecure channel.
Right. Eve can intercept the encrypted message. She can intercept the public key, but she can't decrypt it. Bob is the only person in the world who can, because only he holds D.
This sounds almost too simple, which is why the analogy works so well. The digital mailbox.
It is the perfect analogy. Bob's public key is like a postal slot on a secure mailbox.
Oh.
Anyone in the world can write a letter, walk up to the mailbox, and securely drop their message inside. That's the encryption.
But the only person who can retrieve those letters, the only person who can actually open that box, is Bob, because he holds the private physical key to the lock.
So the communication is private, and the key distribution problem is gone. Alice never needs Bob's secret key.
But this paradigm, it requires a very specialized mathematical structure at its core. It's not enough to just have two keys. The math has to guarantee that knowing the public key tells you absolutely nothing useful about the private key.
Exactly. And that leads us to the concept that underpins all public key systems. The trapdoor function.
A trapdoor function.
Or a one-way function. It's a piece of mathematics defined by being really easy in one direction and extremely difficult in the reverse.
So easy to encrypt.
Right. Calculating the function in the forward direction, our encryption process, has to be computationally fast and easy.
And the reverse.
The reverse calculation, the active decryption without the private key, must be what we call computationally hard. That means using all current computing power, it would take centuries, millions of years, or even longer.
And the private key, the D, that's the trapdoor.
That's the trapdoor. It's the hidden piece of information that turns that mathematically difficult reversal into an instant, easy calculation for the intended recipient.
And so the genius wasn't just coming up with the idea of two keys, but actually finding the right mathematical function that behaves exactly like this computationally asymmetrical trapdoor.
And that foundation was found in the properties of modular arithmetic and prime numbers. The first real implementation of this trapdoor is the RSA algorithm.
Okay, let's unpack this. Let's see how all that abstract number theory we studied actually creates this trapdoor. RSA for Rivest, Shamir, and Adelman, who finally solved this in 1977.
This is where it all comes together.
This is where all those concepts about modular inverses and coprimes finally pay off.
Okay, so we can break RSA down into 4 crucial steps: key generation, public key selection, encryption, and decryption.
Step 1, the foundation of security. Key generation. This is all Bob's secret work.
Bob starts by selecting 2 enormous prime numbers, P and Q. And when we say enormous, we mean primes that are hundreds of digits long. Today, a standard RSA key is 2048 bits, which means N will have around 617 digits.
And the size is critical.
The sheer size is critical because the security rests entirely on the impossibility of reversing this next step.
Okay, so he has P and Q. What's next?
Bob calculates their product. One knowledge is P, the AE. This N is called the modulus, and it forms the working framework for all the math to follow. And crucially, N is public knowledge. It's part of Bob's public key.
So N is public, but P and Q are kept intensely secret. Why is keeping them secret the ultimate security requirement?
Because the next step requires knowledge of P and Q to calculate a hidden value. It's called Euler's totient function, phi1.
Euler's totient.
And if P and Q are prime, calculating a phi is easy. It's just P1 multiplied by Q1 dollar. This value represents the number of positive integers less than n that are coprimed to n. This value is the mathematical key to the whole system's reversibility.
So we have the public modulus n and the secret Euler's totient, phi's in dollar.
Yeah.
We've built the framework, but we don't have the keys yet. What's step 2? Choosing the public exponent e.
Right. Bob now selects a public exponent e. This number can be small. It's often chosen to make the encryption calculation, x to the e, fast for Alice.
But it has to meet a specific requirement.
One specific mathematical requirement, e must be coprime or relatively prime to phi m.
So they share no common factors other than 1.
Exactly. This is what ensures that the inverse key d actually exists. This e along with n forms Bob's public key pair, e any.
Okay, now for the private key, d, the secret trapdoor itself.
The private key d is the multiplicative inverse of e modulo d.
Whoa, okay, let's break that down.
In simpler terms, Bob is solving a specific mathematical equation.
Right.
He is looking for a number d that, when you multiply it by e, leaves a remainder of 1 after being divided by that secret number.
That sounds incredibly complicated to calculate, especially with numbers that are hundreds of digits long. Isn't this supposed to be fast for Bob?
It is fast for Bob because he knows phi any e. The calculation of this modular inverse is performed using the extended Euclidean algorithm.
We've mentioned the Euclidean algorithm before. Why is the extended version so crucial here?
The standard Euclidean algorithm is the most efficient way to find the greatest common divisor of two numbers. The extended version of that algorithm takes that efficiency and just leverages it to find the modular inverse, that key d.
So it's a known fast process.
It's fundamental to RSA's success. If the EEA didn't exist, finding d would be impossibly slow, even for Bob. The EEA guarantees that key generation is nearly instantaneous for the legitimate user.
So to recap Bob's work, the public key is the pair, the private key. His secret trapdoor is the number d. Now we can move to step 3, encryption.
Alice's turn.
Alice has her message, converts it to a number x, and uses Bob's public key.
Yes. She has to make sure her message number x is smaller than n. She then performs the encryption using modular exponentiation. The formula is y equals x n.
So she takes her message x, raises it to the public exponent e, and finds the remainder when divided by the public modulus n.
And that result, y, is the ciphertext she sends.
And that calculation is fast, you said, because e is generally a small number.
Precisely. It happens in milliseconds. Now, Eve intercepts y, n, and e. She knows the formula, but to reverse it, she needs d. And without d, or without factoring n, she's stuck.
Which brings us to step 4, decryption. Bob receives the cryptogram y. He uses his private key d to get the original message.
Bob just reverses the process, but with his secret exponent d, the formula is sexosses yars no.
So he raises the cryptogram y to the power of his massive private key d modulo n.
And here is the magical moment, as you called it. X is mathematically guaranteed to equal the original x.
Okay, and this is the moment where our prior deep dives really pay off. Why does this work? Why does raising y to the power of d perfectly undo raising x to the power of e? What's the guarantee?
The guarantee lies entirely in Euler's theorem. This is the bedrock proof that ensures every message encrypted with E can only be decrypted successfully by that specific inverse D.
Okay, so let's try to get our heads around the mechanism. Bob is calculating NAA, and since y is just $6, what he's actually calculating is x raised to the power of EA2AD.
Correct. The whole system works if sexDEDE simplifies back to x when you take it modulo n.
And the trick, the whole thing, rests on how E and D were designed in the first place.
Exactly. They were specifically generated so that D is the inverse of U modulo. That is the essential link. The structure of that relationship means that the product, E times D, is congruent to 1 when divided by feet.
Okay, so E times D is always equal to 1 plus a multiple of phi dollars. Let's call it multiple K. So 1 phi dot D1 plus K era phi I.
Yes. And now we leverage the power of Euler's theorem. Euler's theorem states that for any number x that is coprime to n, raising x to the power of otito is congruent to 1 $p mod n men.
It's that powerful cyclical property that Bob built into the system.
Right. So when Bob calculates x raised to the power of dia, he is essentially calculating x raised to the power of $1 plus EIS.
And using the rules of exponents, we can just separate that into x to the power of 1 multiplied by x to the power of n.
You got it, which can be rewritten as sextnns times sex EAN, and since sextn is congruent to 1, thanks to Euler, that second part just becomes $1, which is just 1.
It's mathematically beautiful. The decryption calculation becomes x to the power of 1 multiplied by 1, all modulo n. The combined power of E and D just cancels out those massive powers of AND.
Guaranteeing the result is simply the original message, X.
Every single time.
So E and D are inverses in a different modulus, but that inversion is what's powerful enough to ensure that the encryption and decryption processes are inverses in the modulus N. That is the core mathematical genius of RSA. It ensures the circle closes perfectly.
And that reversibility, combined with the extreme difficulty of finding D in the first place, is what makes the system a perfect trapdoor function.
Which brings us to security.
Right. We know the math works. But why can't Eve just find D and break the whole thing? Where exactly does the security of RSA reside?
The security of RSA, unlike the decryption process itself, isn't based on a rigorous mathematical proof of security. It actually rests on a foundational hypothesis. It's about computational complexity.
We're betting on the speed difference between two different computations.
In a way, yes. So let's review the path Eve has to take. She knows the public key, A. To decrypt, she needs the private key, D.
And to find D, she has to know the secret value.
Right, because D is the inverse of E modulo.
Okay.
If she knows E and she knows VIA, calculating D is simple. It's fast. She just uses the extended Euclidean algorithm, which everyone knows.
So the goal for Eve shifts. It becomes find Phi-n. And since Phi-n calculated from the secret primes P and quits P1, key shad, Eve's real task is to find the factors P and Q of the public modulus N.
Precisely. Eve knows N. She knows N is the product of two enormous primes, Q and Q. The entire security system of RSA, which protects, global commerce, relies entirely on one simple fact. For large N, there is no known efficient algorithm for finding P and Q.
That is the factoring problem.
That is the factoring problem.
And our sources highlight this really important relationship. Even if Eve could somehow guess Phi without factoring N directly, she'd still be able to find P and Q.
It's a clean algebraic dependency. If Eve knows both 1$Pven and P1Q-1, she has two equations with two unknowns, P and Q. And she can solve that system using a standard quadratic equation. The primes P and Q would be revealed instantly. So the game is entirely, 100%, centered on the difficulty of that initial factoring step.
To really get a sense of this computational hardness, let's talk about scale again. Bob can multiply two 300-digit primes in milliseconds to get N.
Instantaneous.
Alice can encrypt a message in milliseconds. But for Eve to reverse that, to factor in, she has to perform an incredibly slow task.
I mean, think about the scale of a 2048-bit RSA key. That number N has over 600 digits. Factoring a number of that size using the best-known classical algorithms, like the general number field sieve, would take a staggering amount of time.
How long are we talking?
Estimates run into hundreds of thousands, maybe millions of years, even using massive supercomputer clusters.
It's that asymmetry of the calculation that's the genius. Multiplication is easy. Finding the original pieces of that multiplication is functionally impossible when the numbers get this large.
And that functional impossibility is what we call computational hardness. It's the difference between doing something in a millisecond and doing something in an eternity. We're not saying it's mathematically impossible. We're saying it is practically impossible.
Given our current technology.
Given the current laws of physics and computation, yes.
But this reliance on hardness introduces a vulnerability if that computational landscape ever changes. And that's a huge area of concern, especially with quantum computing.
Absolutely. The foundational hypothesis of RSA security that factoring is hard holds true for classical silicon-based computers. But research into quantum mechanics introduced a potential mathematical bomb, Shor's algorithm.
Shor's algorithm, discovered by Peter Shor. It's a theoretical quantum algorithm designed specifically to find the prime factors of a large number n really, really quickly.
That's the terrifying part. While classical algorithms run in what's called sub-exponential time, meaning the time grows incredibly fast as n gets bigger, Shor's algorithm, if you could run it on a large, stable quantum computer, would factor n in polynomial time.
So millions of years on a classical computer could be reduced to, what, seconds, minutes?
Seconds or minutes on a powerful enough quantum machine, yes.
This is why cryptographers are already developing post-quantum cryptographic standards.
Yeah.
Because the moment a powerful enough quantum computer exists, every secret ever encrypted with RSA that has been stored could potentially be broken.
That thin line we rely on, computational hardness, would just vanish instantly.
So we sleep soundly for now because the tech to run Shor's algorithm at scale doesn't exist yet, but the race is on.
It is. And every time we increase the size of P and Q, going from 1024-bit to 2048-bit keys, We are essentially just buying ourselves more time, buying time against the slow creep of classical computing power and the distant, but maybe inevitable threat of quantum factorization.
The knowledge that our entire global digital security architecture rests on an unproven assumption about the complexity of factoring.
Yeah.
That's both terrifying and utterly fascinating. So, RSA solved the key exchange problem. It provides secrecy based on Euler's theorem, and it relies on the hardest problem in number theory for security. But it has one final trick up its sleeve that makes it indispensable for commerce and law.
Digital signatures.
Digital signatures.
And this is ingeniously simple because it just relies on the same mathematical reversibility, but you reverse the roles of the public and private keys.
Okay, so up until now, we've used the public key, E, to encrypt, and the private key, D, to decrypt. That gives us confidentiality. What happens if Bob uses his private key, D, to start the process?
Well, if Bob uses his private key D to encrypt a message, so YP missed Himmel and a night, the result is no longer secret.
Why not?
Because Bob's public key, ED, is publicly available. Anyone can use E to reverse the calculation. Sexes, Yi Timot, they can read the original message X.
So the goal isn't secrecy anymore, it's proof. The goal is authentication.
Precisely. Only one person in the entire world possesses that private key D. Therefore, the ability to decrypt the message successfully using the public key E serves as irrefutable mathematical proof that the message must have originated from the person who controls D.
Which is Bob.
Which is Bob. It provides non-repudiation. Bob can't later say, I didn't authorize that transaction or I didn't send that contract. The mathematical signature proves his involvement.
And this is the foundation of trust in almost every online transaction. When you download software, the distributor signs it with their private key.
And your computer uses their public key to verify that signature. If it works, your computer knows two things. One, the software came from the legitimate source, and two, that it hasn't been tampered with since it left that source.
Our sources make a good practical point here. We don't usually sign the entire massive document, right? That'd be too slow.
No, you're right. That would be computationally slow. Instead, we use something called a hash function.
A digital fingerprint.
A perfect way to put it. A hash function takes any input, a massive contract, a photo, a terabyte of data, and it spits out a short fixed-length string, maybe 256 bits long. That's the hash value. And even a single comma change in the original document completely changes the resulting hash.
So Bob generates that tiny, unique digital fingerprint of the document. And then he signs only that hash value using his private key D.
That's right. The signature itself is just the signed hash. The verification process for the recipient then has two steps. First, you calculate the hash of the document you received yourself. Second, you use Bob's public key to decrypt the signature he provided.
And if the decrypted value, the original signed hash, exactly matches the hash value you just calculated,
the document is authenticated and untampered.
It's the ultimate mathematical application of that inverse relationship we found in modular arithmetic, just shifted from protecting privacy to ensuring trust and authenticity. It's an incredibly clever and fundamental duality in public key cryptography.
So we have completed the full arc of this deep dive.
Yeah.
We started in the abstract world of number theory, dealing with, the esoteric properties of huge prime numbers, modular inverses, and the elegant power inside Euler's theorem.
And we now see that this purely theoretical math provides the essential backbone for the most practical system in modern security, RSA. It solved that centuries-old key exchange problem. It allowed us to move from the impossible logistics of symmetric key distribution to the globally scalable model of public key infrastructure.
And the ability to factor those massive primes is the fundamental boundary condition for our entire digital world. The ease of multiplication and the near impossibility of factorization that creates the perfect one-way street, the perfect trapdoor.
And that makes secrecy and authentication possible on a scale that cryptographers of the classical era could never have even dreamed of.
They couldn't have.
It truly is the prime payoff for all that intellectual heavy lifting. It's deeply satisfying to trace that line from Euclid's ancient algorithms through Euler's theorems all the way to the little lock icon in your browser today.
And that leads us to our final provocative thought for you to consider as you wrap up this deep dive. While we rely on the computational hardness of factorization, remember that this hardness is an assumption. It's based on classical computing limitations. What happens to trust, security, and the global flow of information if that assumption is ever proved wrong?
Imagine a world where quantum computing breaks through. Or maybe just a novel mathematical technique is discovered that speeds up factorization dramatically. Every encrypted message, every digitally signed contract, every secret key ever generated by RSA would immediately be rendered insecure. The barrier protecting secrets today isn't physical, it's purely mathematical.
The survival of digital security rests on the hope that the difference between multiplying two large primes and factoring their product remains a difference of millions of years.
It's an exhilaratingly high-stakes gamble, something to keep in mind the next time you hit send.